Before we dive into the deep past of our planet, a quick note: if you enjoy calm science-based journeys through Earth's history, it really helps when you like the video, subscribe to the channel, and share it with someone who might enjoy it too. It makes a huge difference, and lets me keep making more episodes like this. Thank you so much for watching, for your time, and for your curiosity. Now let's step back into the Proterozoic and explore the Great Oxidation and Snowball Earth. During the Proterozoic Eon, the planet orbits a middle-aged star that supplies a steady flow of energy over very long spans of time. The sun at this stage shines a little less brightly than in the later Phanerozoic, but its gradual increase in power is slow compared with the geological and biological changes that occur on Earth. The star's output, averaged over millions of years, remains relatively stable, so the amount of energy that reaches the top of Earth's atmosphere varies mainly because of orbital and rotational effects, rather than sudden shifts in stellar behavior. On these timescales, the sun acts as a persistent boundary condition, a distant but reliable source that sets the scale of temperatures and climate without large abrupt jumps in luminosity. Earth follows an orbit that is close to circular, keeping the distance to the sun within a relatively narrow range through each year. Small variations in the shape of the orbit and in the tilt and wobble of the rotational axis occur, but they unfold slowly and cyclically. Over tens of thousands to hundreds of thousands of years, these orbital cycles change how sunlight is distributed between seasons and latitudes, but they do not move the planet sharply closer to or farther from the sun. As a result, the average energy received over the whole sphere of the planet stays within limits that allow liquid water to exist on the surface for most of the Proterozoic. The length of the day continues to increase during this eon, as tidal interactions between Earth and the Moon transfer rotational energy outward. In the early part of the Proterozoic, a full rotation is completed more quickly than in the present day, so there are more shorter days in a given year. As time passes, friction within the oceans and crust gradually slows the spin, so the number of days in a year decreases, while the total amount of sunlight received in that year remains almost unchanged. This slow lengthening of the day influences how heat is distributed across the surface, how long any given region remains in sunlight or darkness, and how strongly the surface warms or cools during each rotation. The tilt of Earth's axis relative to its orbital plane also matters for the Proterozoic boundary conditions. The tilt stays within a moderate range, neither nearly upright nor extremely inclined. Because of this, the cycle of seasons remains significant, but not extreme, with varying solar angles leading to differences between equatorial and polar regions. Over long intervals, slow precessional motions cause the orientation of the axis to trace a circle, changing the timing of seasons relative to orbital position. These cycles alter the pattern of solar heating that reaches different latitudes at different times, a quiet but important influence on long-term climate trends that will later interact with atmospheric and surface changes. The distribution of sunlight over Earth's spherical surface depends on latitude, and this geometric effect is also fixed by the planet's size and shape during the Proterozoic. Equatorial regions always receive sunlight more directly than the poles, so they receive more energy per unit area, while high latitudes are tilted away from the sun for much of the year and receive weaker insolation. This contrast is fundamental to the planet's energy balance and sets up large-scale gradients in temperature that help drive winds and ocean circulation. Even as continents slowly move over the globe, this latitudinal pattern of solar input remains anchored to the geometry of the planet and the distance to the sun. Solar radiation arrives mainly in the form of visible and near-visible light, which passes through the upper layers of the atmosphere and eventually meets the surface or the tops of clouds and ice. After absorption, this energy is re-emitted as longer wavelength radiation, which interacts differently with atmospheric gases. The balance between incoming short wavelength energy and outgoing long wavelength energy defines the radiative budget at the outer edge of the climate system. During the Proterozoic, this balance is shaped by the same basic processes that operate today, but the detailed response of the atmosphere and surface changes as composition and reflectivity evolve. The gravitational relationship among the Sun, Earth and Moon also remains stable over these timescales, ensuring that the planet's orbit is not strongly disturbed by other bodies in the solar system. Large impacts become less frequent than in the earlier Archean, so sudden changes to rotation or orbit become rare. Tides raised by the Moon and the Sun are persistent features steadily converting rotational energy to heat, and slightly altering the length of the day and the distance to the Moon. This slow dynamical evolution is continuous and gentle, compared with the chemical and climatic events that will unfold. The Proterozoic Eon spans roughly from about 2.5 billion years ago to about 500 million years ago, an interval so long that even these gradual orbital and rotational changes accumulate. Yet across this entire span, the basic astronomical setting remains one of relative stability. A slowly brightening sun, an orbit that stays close to circular, a moderate axial tilt and a lengthening day together define the outer frame in which all later atmospheric, oceanic and biological developments take place. These boundary conditions do not determine the detailed path of the planet's history, but they constrain the range of climates that are possible, setting a broad and steady background against which internal changes within Earth systems proceed. Over still longer stretches of time, very slow changes in orbital parameters adjust the contrast between seasons and the contrast between equator and poles. These shifts can favour the growth or retreat of ice sheets when other parts of the Earth system respond, but the cycles themselves remain regular and predictable, adding a repeating rhythm to the flow of solar energy that reaches the planet and completing the description of the Proterozoic cosmic frame. The atmosphere at the beginning of the Proterozoic is a thick dynamic shell of gas that surrounds the planet and links space surface and interior. It is dominated by nitrogen, which is relatively inert and accumulates over long times as volcanic gases and recycled crustal materials add to the air. Alongside nitrogen, carbon dioxide and methane are present in much larger amounts than in later ages and act as important greenhouse gases. Water vapour contributes as well, varying with temperature and with the presence of oceans and ice at the surface. Together, these gases control how much of the Sun's energy is retained in the climate system once it has passed through the upper layers of the atmosphere. Oxygen, by contrast, is only a trace component in most parts of the atmosphere at this stage. Small pockets of air over certain regions, especially shallow coastal seas, with active microbial mats may carry slightly higher oxygen levels, but the background abundance in the global atmosphere remains very low. This reflects the balance between small sources of free oxygen and many efficient sinks that remove it through reactions with gases and rocks that are in reduced or oxygen-poor states. Volcanic activity continually supplies gases such as hydrogen carbon monoxide and reduced sulfur compounds that react readily with any free oxygen that appears. Iron in exposed rocks and in the upper parts of the crust also reacts with oxygen, locking it into mineral forms such as oxides and hydroxides. At the same time, large areas of the ocean are rich in dissolved ferrous iron and other reduced species that can consume oxygen when air and water mix. All of these sinks keep the atmospheric oxygen level low and prevent it from spreading evenly through the entire global air mass. In the upper atmosphere, ultraviolet light from the sun breaks apart some of the molecules present, including water vapour and methane. This photochemistry forms small amounts of new compounds such as ozone, which is a molecule consisting of 3 oxygen atoms. Ozone can build up into a diffuse layer at altitudes where it is produced faster than it is destroyed, and it absorbs ultraviolet radiation. However, in an atmosphere where free oxygen is rare, the ozone layer is thin and less continuous than in later times. This means that ultraviolet light can penetrate more deeply into the atmosphere and reach the lower air and surface with greater intensity, influencing the conditions under which early Proterozoic life exists, especially in shallow water and near the surface of exposed land. Methane plays a larger role in the early Proterozoic atmosphere than it does in later eras. Many microorganisms in low oxygen or oxygen-free environments produce methane as a byproduct of their metabolism, and this gas can accumulate if it is not quickly destroyed. Methane is an effective greenhouse gas and traps outgoing long-wavelength radiation, more strongly than carbon dioxide on a molecule-by-molecule basis. In a world with little oxygen, methane survives for longer periods before it is broken down by sunlight and reactive species in the upper air. This extended lifetime allows methane to reach mixing ratios that significantly affect the thermal structure of the atmosphere. When methane and carbon dioxide coexist at high levels, they jointly shape the vertical temperature profile and determine how heat is transported from the surface to space. The presence of methane and other reduced gases also influences the appearance and optical properties of the atmosphere. Under certain combinations of gas abundances, photochemical reactions can produce hazes made of complex organic particles suspended in the upper layers. These hazes scatter and absorb sunlight, modifying how much energy reaches the lower atmosphere and surface. They can cool the planet by reflecting sunlight back to space, or warm certain layers by absorbing radiation. In the early Proterozoic, the degree to which such hazes form depends on the balance between methane, carbon dioxide, and nitrogen, and on the rate at which ultraviolet light drives chemical change at high altitudes. Below the upper atmosphere, the troposphere holds most of the mass of the air and is the main arena for weather. Here, convection, condensation of water vapor, and large-scale circulation patterns mix the gases and transport heat and moisture. Cloud systems form where air rises and cools, leading to condensation of water droplets or ice crystals. These clouds reflect incoming solar radiation and also trap outgoing infrared radiation, acting as both cooling and insulating layers depending on their type and altitude. In the early Proterozoic, cloud behavior responds to the same physics that operates in later times, but it is embedded in a background of different greenhouse gas concentrations and different distributions of land and sea. The lower atmosphere also interacts continuously with the surface through processes such as evaporation, rainfall, chemical weathering, and gas exchange with soils, rocks, and water bodies. Carbon dioxide dissolves into rainwater and surface waters, forming weak acids that react with minerals in rocks. This chemical weathering removes carbon from the atmosphere and carries it as dissolved ions into rivers and oceans. Over long periods, this process can draw down atmospheric carbon dioxide, especially when tectonic uplift exposes new rock to weathering in warm, wet climates. At the same time, volcanic degacing and metamorphism release carbon dioxide back to the atmosphere, balancing these sinks over millions of years. The early Proterozoic atmosphere is therefore part of a long-term cycle in which carbon moves between air-water crust and mantle. The interface between atmosphere and ocean is a broad moving boundary where gases exchange in both directions. Carbon dioxide enters the surface ocean, where it forms dissolved inorganic carbon species that participate in buffering the alkalinity of seawater and in building carbonate minerals. Methane and other gases produced in marine sediments or water columns can escape to the air, where they alter the greenhouse properties of the atmosphere. In places where there is local production of oxygen by photosynthetic microorganisms near the surface of the ocean, oxygen can leak into the atmosphere, but it is quickly consumed elsewhere by reactions with reduced gases and surfaces. This patchy and transient flow of oxygen from ocean to air further emphasizes how uneven the early Proterozoic atmosphere is in its detailed composition, even as it appears well mixed at the larger scales when viewed from space. The pressure of the atmosphere near the surface is controlled mainly by the total mass of gases present. While the exact value through the Proterozoic is uncertain, the air is dense enough to support liquid water at the surface and to maintain a wide range of weather processes, including storms and long-lived wind patterns. The balance of gases sets the speed of sound, the density profile with height, and the rate at which temperature decreases with altitude. These physical properties influence how air rises and sinks, how clouds form, and how heat is transported vertically. All of these processes operate within the constraints set by the composition of the gas mixture and the incoming solar energy tying microscopic molecular interactions to planetary scale circulation. In summary, the early Proterozoic atmosphere is a nitrogen-rich carbon dioxide and methane-bearing envelope, with very low global oxygen levels shaped by continuous exchange with volcanoes, oceans, rocks, and living organisms. It filters solar radiation, traps heat, and participates in long-term cycles that regulate temperature and chemistry. Its state at the start of the eon provides the baseline from which later shifts in composition and structure arise and forms the surrounding layer through which light and energy must pass before reaching the oceans and continents below. The gradual rise of oxygen in the early Proterozoic atmosphere begins with many small local imbalances between sources and sinks of this reactive gas. In shallow seas and along flooded continental margins, microorganisms that perform oxygenic photosynthesis release molecular oxygen as a byproduct of using sunlight to split water and fix carbon. For long intervals, almost all of this oxygen is consumed close to where it is produced, reacting with dissolved iron in seawater, reduced volcanic gases and exposed minerals at the surface. The global atmosphere above these regions remains largely unchanged in its bulk composition, but thin layers of air just above productive waters can briefly carry slightly higher oxygen levels than the rest of the planet. Over time, as these photosynthetic communities spread and persist, the total amount of oxygen they release increases, and the balance between production and removal slowly shifts. The Great Oxidation Event is not a single moment, but a long interval, during which the average oxygen content of the atmosphere transitions from extremely low values to levels that are still far below modern conditions but high enough to alter surface chemistry and climate. Estimates of the exact timing and shape of this rise vary, and the rock and isotope record suggest that the path includes steps, pauses, and possible partial reversals. However, the central picture is that over hundreds of millions of years near the Archean Proterozoic boundary and into the early Proterozoic, the combined action of many small oxygen-producing ecosystems gradually overwhelms the most accessible sinks. As reduced iron in surface oceans becomes more fully oxidized and buried, and as reactive volcanic gases are consumed, more of the newly produced oxygen survives long enough to escape into the wider atmosphere instead of being removed near its sources. As oxygen begins to accumulate, the chemistry of the atmosphere adjusts. Methane, which is abundant in a low oxygen world, reacts readily with oxygen, and with oxidizing radicals that form more frequently as oxygen becomes available. These reactions lower the lifetime and concentration of methane in the air. Because methane is a strong greenhouse gas, even modest reductions in its abundance can influence the thermal structure of the atmosphere and the surface climate. At the same time, oxidation of sulfur and nitrogen containing gases alters the mixture of aerosols and trace compounds, changing how sunlight is scattered and absorbed in different atmospheric layers. The decline of methane also affects the formation of photochemical hazes. In earlier, more reducing conditions, complex organic particles can form in the upper atmosphere, producing a haze that reflects and absorbs sunlight. As oxygen levels rise and methane levels fall, the rate at which such hazes form decreases, and the character of the upper atmosphere shifts toward clearer conditions. This, in turn, changes how much solar radiation reaches the lower atmosphere and surface, and how it is distributed with height. The transition is not necessarily smooth or globally uniform. Local differences in volcanic activity, ocean circulation, and biological productivity mean that some regions experience higher oxygen levels earlier than others. In certain coastal environments and shallow seas, oxygenated surface waters may come into contact with the atmosphere for extended periods, favouring stronger exchange between water and air. In contrast, large parts of the deep ocean and some low-lying basins remain anoxic and rich in reduced species that continue to consume oxygen that diffuses or mixes downward. The global atmosphere averages over these local variations, but the pattern of change is patchy and complex when examined in detail. As oxygen slowly becomes a more significant fraction of the atmosphere, new pathways for chemical reactions open. One important consequence is the growth of a more substantial ozone layer in the stratosphere. Ozone forms when molecular oxygen absorbs ultraviolet light and splits into single atoms which then recombine with other oxygen molecules. When enough oxygen is present, this process can sustain a layer in which ozone concentration is high enough to absorb a large share of incoming ultraviolet radiation. During and after the Great Oxidation Event, this developing ozone shield reduces the flux of biologically damaging ultraviolet light that reaches the lower atmosphere and surface, especially on land and in the uppermost layers of the ocean. This change in the radiation environment alters the conditions under which surface and near-surface life exists, even if many organisms remain adapted to low oxygen niches. The presence of more oxygen in the air also affects the oxidative capacity of the atmosphere, a term that refers to its ability to degrade and transform reduced gases. As reactive oxygen-containing molecules become more common, they participate in chains of reactions that break down organic vapors and trace gases into more oxidized products. These products may remain in the gas phase or condense into particles that act as cloud condensation nuclei. By influencing the number and properties of atmospheric particles, rising oxygen levels can modulate cloud formation, cloud brightness, and the vertical distribution of moisture and latent heat. Such links between chemistry and cloud microphysics contribute to the gradual reorganization of the climate system that accompanies the change in atmospheric redox state. Throughout the early stages of this transition, oxygen remains a minor component by volume compared with nitrogen and even with carbon dioxide, but its reactivity means that small changes in abundance have large effects on surface environments. The precise level of oxygen reached during and immediately after the Great Oxidation Event is uncertain. Many lines of evidence indicate that it stabilizes at values far below present atmospheric levels, yet sufficiently high to prevent a return to the extremely reducing conditions that prevailed earlier. Once this new baseline is established, short-term fluctuations may occur as volcanic emissions, weathering rates, and biological productivity vary, but the overall direction has shifted. The atmosphere now contains enough oxygen to leave a clear imprint on mineral sediments and isotopic compositions, and to support new combinations of metabolic pathways for life in surface and near-surface settings. In this way, the Great Oxidation Event marks a long but decisive adjustment of the atmosphere from a nearly oxygen-free state to one that is persistently, though modestly, oxygen-bearing, setting the stage for further coupled changes in oceans, rocks and ecosystems later in the Proterozoic. As the composition of the atmosphere changes during the early Proterozoic, the climate system at the surface responds over long timescales that involve the ocean's ice cover and the overall reflectivity of the planet. The gradual decline of methane that follows the rise of oxygen reduces the strength of the greenhouse effect, especially in the upper atmosphere, where methane once absorbed a large fraction of outgoing long-wavelength radiation. Carbon dioxide remains an important greenhouse gas, but if its concentration does not increase enough to compensate, the net effect is a decrease in the capacity of the atmosphere to retain heat. At the same time, the reduction of organic hazes that were sustained by high methane levels allows more sunlight to reach the lower atmosphere and surface, but this gain in incoming short wavelength energy can be outweighed by the stronger loss of long wavelength energy to space. The balance between these processes is delicate, and on long timescales, small shifts can tilt the climate toward cooler states. The distribution of continents and oceans also plays a role in shaping the early Proterozoic climate. Large land masses are thought to be present at a range of latitudes including near the equator, and in higher latitudes, although their exact configurations and positions evolve with ongoing plate motions. When continents lie at low latitudes, they receive relatively intense sunlight, and their surfaces can warm strongly during the day. However, if these land areas are subject to chemical weathering under warm and wet conditions, they can draw down carbon dioxide from the atmosphere through reactions with silicate minerals, a process that removes greenhouse gas and stores carbon in dissolved form and in sediments. Over millions of years, this enhanced weathering can contribute to a decline in atmospheric carbon dioxide and promote cooling, especially when combined with the reduction in methane driven by rising oxygen. As global temperatures gradually fall, snow and ice can expand beyond their earlier limits. At high latitudes where insulation is already weaker, glaciers and ice sheets may grow on land while sea ice spreads across polar oceans. Ice and snow surfaces reflect a larger fraction of incoming sunlight than open water or bare rock, raising the planetary albedo. This increase in reflectivity means that a greater portion of solar energy is returned directly to space without warming the surface or atmosphere. The reduced absorption of sunlight further lowers temperatures, which allows ice to expand still more, continuing the cooling trend. This interaction between temperature and ice cover operates as a positive feedback within the climate system, where initial cooling promotes more ice, and more ice promotes further cooling. In the early Proterozoic, such feedbacks contribute to extended glacial intervals, including the long Huronian glaciation. During this time, evidence suggests that large parts of the planet experience cold conditions for tens of millions of years, with continental glaciers advancing to relatively low latitudes and widespread glacial deposits forming on land and in marine basins. The exact geographic extent and severity of the ice cover remain under study, but indicators such as striated bedrock dropstones and characteristic sedimentary layers point to repeated advances and retreats of ice. These deposits record a climate system that is capable of maintaining extensive frozen regions and of reorganizing ocean and atmospheric circulation in response. The growth of ice sheets alters wind patterns and storm tracks by changing the temperature gradients between equator and poles. Cold, high-altitude ice surfaces over continents create strong pressure differences with adjacent ice-free regions, guiding the paths of cyclones and influencing precipitation patterns. In many areas, precipitation falls as snow that adds mass to ice sheets, while in other regions, arid conditions may develop as moisture is diverted or locked up in ice and snow. At the same time, sea ice cover over polar and possibly mid-latitude oceans solidifies the upper layers of the ocean and reduces direct contact between the atmosphere and liquid water. This barrier weakens the exchange of heat gases and moisture between ocean and air, altering the rate at which the ocean can buffer climate changes. Beneath the ice, the ocean continues to transport heat and salt, but the pattern of circulation may differ from earlier warmer conditions. Stratification between surface and deeper waters can intensify as cold, relatively fresh meltwater overlays denser saltier water, or as brine rejections during sea ice formation drive sinking of very saline water masses. These changes in ocean structure influence how heat is stored and released, and how dissolved gases including carbon dioxide and oxygen are moved between regions. Volcanic and tectonic processes continue during glacial intervals, emitting carbon dioxide and other gases into the atmosphere. Over long timescales, this volcanic input can build up greenhouse gas levels if weathering and biological uptake are reduced by cold conditions and limited liquid water in some regions. When glaciers cover large areas of continental crust, they shield underlying rocks from direct weathering and reduce the efficiency of the silicate weathering sink. If volcanic emissions persist under such circumstances, carbon dioxide can gradually rise, even while the surface remains cold, eventually contributing to a weakening of the glacial state. Thus, the same tectonic processes that may once have helped to lower carbon dioxide when continents were exposed can later play a part in bringing a prolonged ice age to an end by providing a steady source of greenhouse gases that are no longer fully balanced by sinks. During the long, early Proterozoic cooling episodes, the planet's climate system continues to operate under the same astronomical boundary conditions described earlier. Seasonal cycles persist with variations in sunlight across latitudes and throughout the year, but the presence of extensive ice and snow modifies how these seasonal inputs are expressed at the surface. In regions dominated by ice sheets, seasonal temperature swings may be damped by the high reflectivity and thermal inertia of thick ice, while in lower latitude regions near the margins of ice cover, small shifts in seasonal insolation can influence the advance or retreat of glaciers. Orbital variations on timescales of tens to hundreds of thousands of years modulate these effects, potentially pacing the timing of glacial maxima and minima within the broader cold interval. Even within a generally cold climate, spatial differences remain. Equatorial oceans that are not fully covered by ice can retain relatively milder conditions with open water or seasonally variable sea ice. Areas near active tectonic boundaries or volcanic regions may experience local warming due to geothermal heat flow and hydrothermal activity. These variations create a range of environments across the planet, from thickly glaciated continents to partially ice-covered seas and regions where liquid water persists at the surface. The overall picture of the early Proterozoic icehouse climate is therefore one of a planet that responds sensitively to changes in atmospheric greenhouse gases and surface reflectivity, and that can sustain long-lasting cold states when feedbacks between ice albedo and radiative balance are engaged. Once the equilibrium between incoming solar radiation, outgoing long-wavelength radiation, greenhouse gas levels and surface reflectivity settles into a configuration that favours low temperatures, the climate system can remain in that configuration for extended periods until slow processes such as volcanic outgassing and continental rearrangement shift the balance again. The Huronian glaciation and related early Proterozoic cold intervals illustrate how, under the same external solar and orbital conditions, internal changes in atmospheric composition and surface characteristics can lead to climate regimes very different from those of earlier and later times, while still operating within the same broad physical principles that govern energy flow through the Earth system. The long middle part of the Proterozoic is often described as a time when surface climate shows fewer dramatic swings than in the earlier and later parts of Earth's history. Over roughly 1 billion years, beginning after the early Proterozoic glaciation subside and extending well into the later Proterozoic, the planet settles into states that, while not unchanging, remain within a narrower range of global temperatures. The astronomical conditions are the same as before, with a slowly brightening sun and regular orbital cycles, but the balance between greenhouse gases, surface reflectivity and heat transport appears to reach configurations that do not lead to sustained extremes of global freezing or overheating. In this interval, large long-lived ice sheets leave fewer traces in the rock record than in earlier Huronian times or in later Neoproterozoic episodes, suggesting that continental scale glaciations are less common or less extensive. Instead, climate indicators point to long periods when average surface temperatures are moderate enough to keep most low-latitude regions ice-free, while polar and high-altitude areas may host smaller, more transient ice caps and mountain glaciers. The absence of widespread glacial deposits in many mid-Proterozoic sequences is one of several lines of evidence that support the idea of relatively stable climate states, though local and regional variations still occur driven by shifting continents and changes in ocean circulation. The composition of the atmosphere during this time continues to evolve, but in ways that tend to maintain a broad radiative balance. After the initial Great Oxidation interval, oxygen remains present at low but non-negligible levels, while methane is kept at lower concentrations than in the very early Proterozoic because of the more oxidizing character of the air. Carbon dioxide continues to act as the main long-lived greenhouse gas. Volcanic outgassing and metamorphic processes supply carbon dioxide to the atmosphere, while silicate weathering on continents and burial of carbonate minerals remove it. Over long periods, the rates of these sources and sinks can nearly match, leading to a kind of dynamic balance in which atmospheric carbon dioxide fluctuates, but does not drift steadily toward very high or very low values. In such a regime, the greenhouse effect is strong enough to prevent pervasive glaciation, but not so strong as to push the planet into a persistently hot state. Ocean cover remains extensive, and the distribution of continents gradually changes as tectonic plates move. Supercontinents assemble and break apart on timescales of hundreds of millions of years, reorganizing the patterns of land and sea that interact with the atmosphere. When large continental masses cluster near the equator, they alter the energy balance because land surfaces respond more quickly to heating and cooling than oceans do, and they enhance silicate weathering in warm, wet tropical climates. When continents shift toward higher latitudes, they can support more snow and ice cover reflecting more sunlight, and cooling those regions. These shifts influence regional climates, and may drive slow changes in global mean temperature, but within the mid-Proterozoic interval, they tend to remain within ranges that do not trigger persistent global-scale icehouse states. In the atmosphere, the ozone layer that began growing during and after the Great Oxidation Event becomes a more persistent feature, absorbing a significant fraction of incoming ultraviolet radiation. This stabilizes the upper atmospheric temperature structure and reduces ultraviolet flux at the surface, especially over land and in the uppermost ocean. The presence of this filter modifies how solar energy is partitioned between wavelengths and heights, but it does not on its own cause large swings in climate. Instead, it contributes to a more regular radiative environment, in which weather systems, storm tracks, and seasonal cycles operate under broadly similar conditions for long spans of time. Cloud formation and large-scale circulation distribute heat and moisture from equator to poles in ways that are familiar in outline, though. The exact strength and position of circulation cells vary with the arrangement of continents and sea ice. The oceans, which cover most of the planet, act as a large reservoir of heat and dissolved substances throughout this interval. Surface waters absorb solar energy and exchange heat and gases with the atmosphere, while deeper waters circulate on timescales of thousands of years, transporting heat from low to high latitudes and from surface to depth. In a climate without extreme lasting ice cover over the low latitudes, this circulation can remain vigorous, smoothing out regional temperature differences and helping to keep the climate system within moderate bounds. Sea level changes as ocean basins adjust to tectonic processes and as thermal expansion or contraction of seawater occurs, but the absence of very large, long-lived ice sheets for much of this time means that ice-driven sea level swings are probably smaller than during major glacial intervals. On land, the weathering of exposed rocks continues at rates that depend on temperature, rainfall, and relief. In warm, humid regions, chemical weathering is active, consuming carbon dioxide from the atmosphere and releasing ions that eventually reach the sea. In cooler or more arid regions, physical weathering and erosion dominate moving material downslope into basins. Over geological timescales, these processes help to regulate atmospheric carbon dioxide by linking the carbon cycle to the uplift and erosion of continents. When uplift exposes fresh rock, weathering rates can increase drawing down carbon dioxide until cooler conditions slow the reactions. When relief is reduced or climates are dry, the drawdown weakens, allowing volcanic sources of carbon dioxide to gradually raise atmospheric levels again. This feedback contributes to the long-term stability of mid-Proterozoic climates by resisting large departures from states where liquid water and active weathering are widespread. Local and regional climates during this billion-year span likely show a range of conditions from tropical shelves with warm shallow seas to cooler high-latitude or high-altitude areas with seasonal snow. Monsoon-like wind patterns may develop where large land masses cross the tropics, bringing distinct wet and dry periods to continental interiors. Coastal zones may experience frequent storms and variable rainfall. Inland basins can range from humid lowlands to more arid regions depending on their position, relative to mountains and prevailing winds. These variations reflect the interplay of global circulation with regional geography, yet they unfold against a background of global mean temperatures that, according to current interpretations of the rock record, do not swing as often into extreme cold or extreme heat as in some other parts of Earth's history. Over the course of this long middle Proterozoic interval, the climate system therefore functions as a slowly shifting but broadly stable framework. The planet experiences changes in continental positions, sea levels, and regional climates, and the composition of the atmosphere and oceans continues to evolve, but the overall surface conditions remain compatible with widespread liquid water, active weathering, and long-lived shallow seas. These relatively steady climates provide a persistent outer setting for the gradual chemical and biological changes that occur within the oceans, and on the continents changes that proceed under a climate that, while not static, stays within moderate bounds for many hundreds of millions of years. The Proterozoic oceans form a connected global system of basins and passages that store most of the planet's surface water and a large part of its heat and dissolved substances. Their structure is set by gravity rotation wind stress and the input of fresh water and salts. But it is also shaped by the density contrasts that arise from differences in temperature and salinity. In this eon, as in later times, surface waters are mixed by winds and waves into a layer that exchanges directly with the atmosphere, while deeper waters are more isolated and can preserve distinct chemical conditions for long periods. The contrast between these layers is important for understanding how oxygen, iron, sulfur, carbon, and nutrients are distributed through the oceans and how they respond to changes in atmosphere and climate. After the Great Oxidation Event, surface ocean waters in many regions become at least weakly oxygenated, especially where contact with the atmosphere is strong and where photosynthetic microorganisms continually produce oxygen in the upper sunlit zone. In these waters, dissolved oxygen can react with reduced species such as ferrous iron and sulfide, converting them to oxidized forms that either remain dissolved in limited amounts or precipitate as solid minerals. This process tends to strip the surface layer of large pools of dissolved ferrous iron that were common in earlier, more anoxic oceans. As a result, the clear separation between oxygen, rich surface waters, and oxygen-poor deeper waters grows sharper, and a boundary sometimes called a redoxcline develops between them. The term redox refers to the balance between oxidized and reduced chemical states, and the position of this boundary depends on factors such as biological activity mixing and the supply of reactive substances from below. Beneath the surface mixed layer, large parts of the Proterozoic deep ocean remain anoxic, meaning that dissolved oxygen is effectively absent. In many basins, these deep waters are also ferruginous, a term that describes waters rich in dissolved ferrous iron. The combination of limited overturning continuous input of reduced iron from hydrothermal vents and seafloor weathering, and the absence of oxygen, allows ferrous iron to accumulate to high concentrations. Organic matter that sinks from the surface is decomposed in these waters by microorganisms that use alternative electron acceptors instead of oxygen, such as sulfate or carbon dioxide, further maintaining reducing conditions. The boundary between oxygenated and ferruginous layers can be relatively shallow over some continental shelves and much deeper in open ocean settings, and it can migrate over time as climate circulation and productivity change. In addition to ferruginous conditions, parts of the mid-depth ocean and some restricted basins may become euxinic, meaning that they are both anoxic and rich in dissolved sulfide. Euxenia arises when the supply of sulfate from the weathering of continental rocks and from hydrothermal inputs is high enough, and when bacterial reduction of sulfate in organic rich waters produces large amounts of sulfide. In such settings, ferrous iron can react with sulfide to form iron-sulfide minerals, removing iron from solution and allowing sulfide to remain abundant. These sulfidic waters are strongly reducing and can host communities of microorganisms adapted to using sulfide and other reduced species in their metabolisms. The extent and persistence of euxinic conditions in the Proterozoic oceans are subjects of ongoing study, but available evidence suggests that euxenia may be common along some productive continental margins and in certain basins, especially during parts of the mid-Proterozoic. The chemistry of Proterozoic seawater is also influenced by the balance of major ions, such as calcium, magnesium, sodium chloride, and sulfate. Rivers deliver dissolved ions from weathered continental rocks to the oceans, while hydrothermal systems at mid-ocean ridges and within the crust exchange elements between seawater and newly formed oceanic crust. Evaporation and precipitation of minerals in restricted basins can concentrate or remove ions locally. Over geological timescales, these processes adjust the total inventories of different ions and set the saturation state of seawater with respect to minerals such as calcium carbonate and various iron and manganese oxides. In moderately oxygenated surface waters, calcium carbonate can precipitate either inorganically or with biological assistance, forming sediments on the seafloor that store carbon and help control the long-term carbon cycle. The relative scarcity or abundance of some ions also influences the availability of essential nutrients such as phosphate that limit biological productivity in many regions. Stratification, or the layering of waters with different densities, is a persistent feature of the Proterozoic oceans. Warm, fresh surface waters can overlie cooler, saltier deep waters, creating a stable density gradient that resists mixing. When stratification is strong, it can reduce the upward flux of nutrients from deep waters to the surface, slowing primary production in the sunlit zone once local nutrient supplies are exhausted. At the same time, it can prevent oxygen produced near the surface from penetrating to depth, allowing anoxic or ferruginous conditions to persist in deep basins. Conversely, when cooling wind stress or changes in salinity weaken stratification, mixing events can transport nutrients from the depth to the surface and carry oxygen downward, temporarily altering the redox structure. The balance between stratification and mixing therefore plays a central role in setting the vertical distribution of oxygen and key elements in the Proterozoic seas. Ocean circulation connects different basins through surface currents, deep flows, and intermediate water masses that move along density surfaces. The patterns of this circulation depend on the positions of continents, the shape and depth of ocean basins, and the gradients of temperature and salinity between regions. In the Proterozoic, when the deep ocean is largely anoxic and ferruginous, deep currents carry iron-rich waters across great distances, linking hydrothermal source regions with faraway basins. Upwelling along some continental margins and in equatorial divergence zones can bring these deep waters closer to the surface, where contact with oxygenated layers leads to oxidation of ferrous iron and other reduced species. This process not only affects local water chemistry, but also influences the deposition of iron-rich sediments on continental shelves and slopes, tying the internal dynamics of the ocean to the rock record that will later be examined at the surface. Temperature in the Proterozoic oceans responds to the balance between incoming solar radiation heat exchange with the atmosphere and internal heat transport by currents. In the long mid-Proterozoic interval of relatively stable climates, sea surface temperatures at low latitudes are warm enough to support vigorous evaporation and convection, while high latitude and deep waters are cooler. During extended glacial periods such as the Huronian and later Neoproterozoic episodes surface waters, in many regions cool and freshen, and sea ice can form over large areas capping the ocean and modifying surface salinity. These changes in temperature and salinity fields adjust the density structure of the ocean, and thus the pattern of circulation affecting how quickly deep waters are renewed and how chemical gradients evolve. Even in cold states, however, geothermal heat flow, hydrothermal activity and slow mixing maintain liquid water beneath any ice cover, preserving an environment in which chemical and biological processes continue. Throughout the Proterozoic, the oceans act as the main reservoir and mixing space for many elements central to the planet's redox balance. They receive reduced substances from the interior and from weathering expose them to oxidizing agents in surface and shallow, subsurface layers, and redistribute the products of these reactions through circulation and sedimentation. The vertical and horizontal redox gradients that arise in this setting are not static. They shift in response to variations in atmospheric composition, climate tectonics, and biological activity. Nevertheless, a recurring pattern persists in which oxygenated surface waters overlie anoxic or ferruginous deeper waters, with zones of strong chemical change between them. This layered structure of the Proterozoic oceans provides the immediate environment in which later changes in rocks, element cycles, and microscopic life will play out, and it frames the context for the Great Oxidation Event and the Snowball Earth episodes within the global water column itself. The solid surface of the planet during the Proterozoic records the slow rise of oxygen and the associated changes in climate and oceans in a layered archive of rocks. Continents made of buoyant crust stand above the denser oceanic crust and carry terrains of older Archean rocks as well as younger Proterozoic formations. As tectonic plates collide and separate these continents, assemble into larger masses, and then break apart again, creating mountain belts, sedimentary basins, and broad continental shelves. In these settings, sediments accumulate bury older surfaces and preserve information about the atmosphere, oceans, and ice that once interacted with them. Over hundreds of millions of years, this steady accumulation builds a stratified record that later allows the timing and nature of the Great Oxidation Event and early glaciations to be inferred. One of the most notable features of this record is the presence and later decline of banded iron formations, which are layered chemical sediments rich in iron oxides. These rocks typically show repeated thin bands of iron-rich material interlayered with chert-to-silica-rich rock. In earlier Archean times, such formations are widespread, reflecting oceans that contain large amounts of dissolved ferrous iron. During and after the onset of increased oxygen production by cyanobacteria oxygenated surface waters, and the mixing of these waters with deeper iron-rich layers cause ferrous iron to be oxidized to ferric iron, which is less soluble and tends to precipitate as iron oxide minerals. These precipitates settle to the seafloor and form the iron-rich layers observed in banded iron formations. As oxygen production continues and the main pools of dissolved ferrous iron in the surface and upper deep ocean become depleted, the rate at which banded iron formations accumulate declines. In many regions, the abundance of large typical banded iron formations decreases after the early Proterozoic, suggesting that the oceans no longer hold the same vast reservoirs of dissolved ferrous iron under oxygen-poor conditions. This change in the character and frequency of iron-rich chemical sediments is one of the signals that the redox state of the global ocean and atmosphere has shifted. It indicates that surface and near-surface waters have become more oxidizing, limiting the ability of ferrous iron to stay in solution and altering the way iron moves through the Earth system. On land, ancient soils known as paleosols also record changes in atmospheric oxygen. Paleosols form when rocks at the surface are exposed to airwater and biological activity long enough to undergo chemical weathering in place. The minerals in the original rock are altered, and new minerals including iron-bearing oxides and clays form in the weathering profile. In very low oxygen atmospheres, iron in the parent rock can remain in more reduced forms as weathering proceeds, and certain minerals that are unstable in oxygen, rich conditions can persist. As oxygen levels rise, iron in exposed materials is more likely to oxidize to ferric forms, and some reduced minerals become less stable and are removed or replaced. By examining the mineralogy and chemical composition of Proterozoic paleosols, researchers infer that a shift from extremely low to modestly higher oxygen levels occurs near the Archean Proterozoic boundary and into the early Proterozoic. The presence of strongly oxidized paleosols of certain ages suggests that, at least intermittently, the lower atmosphere above land surfaces holds enough oxygen to drive extensive oxidation of iron and other elements. Another line of evidence comes from sulfur-bearing sediments. In the Archean, many sedimentary rocks show a pattern in the relative abundances of sulfur isotopes known as mass-independent fractionation, which is thought to arise from photochemical reactions in an atmosphere with very little oxygen and no substantial ozone shield. As oxygen rises and ozone becomes more abundant in the stratosphere, these photochemical pathways change, and the characteristic mass-independent pattern largely disappears from younger sediments. The loss of this signal in early Proterozoic sulfur deposits is consistent with a shift to an atmosphere that has crossed a threshold oxygen level, even if the absolute concentration of oxygen remains well below modern values. Together with the iron and paleosol records, the sulfur isotopes provide a coordinated view of a planet whose surface environments are becoming more oxidizing over time. Sediments recording glaciation also appear in the early Proterozoic rock record and help to define the extent and nature of cold intervals such as the Huronian glaciation. Glacial tillites, which are poorly sorted sediments deposited directly by ice, contain a mixture of grain sizes from fine mud to large boulders. On land, these deposits can rest on bedrock surfaces that show striations and grooves carved by moving ice. In marine settings, dropstones preserved in finer-grained sediments indicate icebergs that carried rocks from land and released them as they melted. The age and distribution of Proterozoic glacial deposits on multiple continents suggest that ice sheets reach relatively low latitudes during some intervals, implying large-scale climatic cooling. These rocks also record transitions from glacial to non-glacial conditions, with overlying layers of more typical marine or continental sediments, marking times when ice retreats and different environments return. Carbonate rocks, particularly those deposited on continental shelves and in shallow marine environments, offer additional information about the chemistry of seawater and the carbon cycle. Calcium carbonate precipitates either directly from seawater or with biological assistance from microorganisms that form shells and skeletons. The relative abundances of stable carbon isotopes in these rocks reflect the balance between organic carbon burial and inorganic carbon cycling. In the Proterozoic, shifts in carbon isotope ratios across stratigraphic sequences are interpreted as changes in the rates at which organic matter is buried and preserved versus respired back to carbon dioxide. Periods when more organic carbon is buried can lead to a net release of oxygen to the atmosphere and are thus linked to the long-term evolution of oxygen levels. The thickness, continuity, and composition of Proterozoic carbonate platforms record extended intervals of relatively stable sea level and climate, as well as episodes of environmental change that alter the sites and conditions of carbonate deposition. Tectonic activity influences all of these records by controlling where basins form, how deep they are, and how long they persist. When continents collide, they create mountain belts that supply large amounts of sediment to nearby basins. The erosion of these mountains exposes fresh rock to weathering affecting the carbon and sulfur cycles, and the delivery of ions and particles to the oceans. When continents rift and separate, new passive margins develop with broad shelves, where thick sequences of shallow marine sediments, including carbonates and shales, can accumulate. These shelves are often sites where banded iron formations, organic rich muds, and later glacial deposits are preserved in stacks that capture long histories of environmental change. The vertical order of these layers from older Archean basement through early Proterozoic, banded iron formations and glacial deposits into mid-Proterozoic carbonates and shales, and beyond reflects the interplay among tectonics, sea level climate and redox evolution. Within these sedimentary sequences, fine-scale features also carry information. Laminated iron-rich beds, thin layers of volcanic ash, microfossil, rich horizons, and changes in grain size or mineral content all mark shifts in local conditions. Some intervals show evidence of anoxic bottom waters and high organic preservation, while others indicate better ventilated conditions with more oxygen reaching the seafloor. By comparing these details across multiple regions and continents, a broad picture emerges of Proterozoic Earth, in which oxygen slowly becomes a more persistent presence in surface environments. Glaciations leave distinctive imprints in scattered but significant intervals, and carbonate platforms document the restructuring of the carbon cycle. The rock record thus preserves in physical and chemical form the cumulative outcome of interactions among atmosphere, ocean ice, and life, and it provides the material evidence for reconstructing the timing and nature of the Great Oxidation Event and its associated environmental changes. The major element cycles of carbon, sulfur, iron, and oxygen during the Proterozoic form a linked network of reactions that connect the atmosphere, oceans, rocks, and living organisms. At the most basic level, these cycles involve oxidation, and reduction often shorten to redox, in which elements gain or lose electrons and change chemical form. In a more reducing environment, elements such as iron and sulfur exist mainly in lower oxidation states, while in a more oxidizing environment, they are converted to higher oxidation states. The balance between reduced and oxidized forms in each reservoir is controlled by the rates of processes that supply and remove them, including volcanic degassing, weathering of rocks, biological activity, and burial of minerals and organic matter. Over Proterozoic timescales, slow changes in these rates shift the redox state of the surface Earth system, contributing to the rise of oxygen and to the evolving character of oceans and sediments. The carbon cycle links volcanic outgassing of carbon dioxide, weathering of silicate and carbonate rocks, dissolution, and precipitation of carbonates in the oceans, biological fixation of carbon into organic matter and burial, and metamorphism of that carbon in deep sediments. Volcanic and metamorphic processes release carbon dioxide from the mantle and crust into the atmosphere. This gas dissolves in rainwater and surface waters to form carbonic acid, which reacts with silicate minerals in rocks during weathering. The products of these reactions, including bicarbonate and various cations, are transported by rivers into the oceans, where they contribute to the dissolved inorganic carbon pool and to the formation of carbonate minerals such as calcium carbonate. When carbonate sediments accumulate and are buried, carbon is stored in solid form for long periods. At the same time, photosynthetic organisms in the surface ocean use carbon dioxide dissolved in seawater to build organic compounds. When a portion of this organic matter sinks and is buried without being fully decomposed, it constitutes a burial of reduced carbon. This burial effectively removes carbon and associated reducing power from the surface system and allows free oxygen produced by photosynthesis to remain in the atmosphere and oceans. The relative amounts of carbon buried as organic matter versus carbon stored as carbonates influence the long-term oxygen budget. If more organic carbon is buried, more oxygen can accumulate. If less organic carbon is buried, more oxygen must be used to oxidize organic matter, and atmospheric oxygen levels are constrained. In the Proterozoic, variations in organic carbon burial are inferred from stable carbon isotope ratios in sedimentary carbonates and organic matter, and these variations are linked to changes in biological productivity, ocean redox structure, and tectonic settings that control the creation of sedimentary basins. The sulfur cycle operates in parallel with the carbon cycle and is closely tied to the redox state of the oceans. Sulfur enters the surface system through volcanic gases, mainly as reduced species such as hydrogen sulfide and sulfur dioxide, and through the weathering of sulfide minerals in rocks. These inputs supply sulfate and sulfide to rivers and oceans. In oxygenated surface waters, sulfur tends to exist mainly as sulfate, a highly oxidized form. In deeper anoxic waters and sediments, microorganisms use sulfate as an electron acceptor in a process called sulfate reduction, converting sulfate into sulfide while oxidizing organic matter. The produced sulfide can react with dissolved ferrous iron to form iron sulfide minerals, which are buried in sediments and store reduced sulfur. The relative balance between sulfate in seawater and sulfide in sediments influences the overall redox budget because burial of iron sulfide removes reduced sulfur from the surface system, leaving more oxidizing power in the form of sulfate and oxygen. Stable sulfur isotope measurements in Proterozoic rocks show shifts from Archean patterns dominated by mass-independent fractionation to Proterozoic patterns dominated by mass-dependent fractionation, indicating that the atmospheric sulfur cycle is now mediated by an ozone-containing oxygen-bearing atmosphere and that extensive microbial sulfate reduction is occurring in the oceans. In many Proterozoic settings, the coexistence of an oxygenated surface ocean and sulfidic deeper waters suggests that sulfate reduction and iron sulfide formation are significant sinks for both organic carbon and iron. The iron cycle in turn reflects the balance between sources of ferrous iron from the interior and sinks in the oceans and sediments. Hydrothermal vents along mid-ocean ridges and within oceanic crust release ferrous iron into seawater, especially into the deep ocean. Weathering of iron-bearing rocks on land also supplies iron to rivers and coastal seas. In an anoxic or weakly oxidizing ocean, this ferrous iron can remain dissolved and transported over long distances. When it reaches oxygenated waters or when local oxygen production occurs in the surface layer, ferrous iron is oxidized to ferric iron, which is less soluble, and tends to form particulate iron oxides and hydroxides. These particles settle to the seafloor and contribute to the formation of iron-rich sediments, including banded iron formations in earlier times and thinner iron-rich beds and concretions later. When sulfide is present in anoxic waters or sediments, ferrous iron can instead react with sulfide to form iron sulfide minerals such as pyrite. The relative importance of these two pathways, oxide formation and sulfide formation, depends on the availability of oxygen and sulfide. In more ferruginous conditions, iron oxides dominate. In more euxinic conditions, iron sulfides are more common. The total burial of iron in these forms influences the redox budget, because iron oxides and iron sulfides store different combinations of oxidized and reduced elements, and their burial removes either oxidizing or reducing equivalents from the active surface system. Oxygen itself participates in many of these reactions as both a product and a reactant. It is produced by oxygenic photosynthesis primarily by cyanobacteria, and later by other photosynthetic groups in the sunlit surface ocean and in shallow waters over flooded land. It is consumed when reduced volcanic gases such as hydrogen and methane are oxidized in the atmosphere, when reduced minerals such as ferrous iron in rocks and sediments are oxidized, and when organic matter is respired by aerobic organisms or oxidized by abiotic processes. Over Proterozoic timescales, the net accumulation of oxygen in the atmosphere and oceans depends on whether the sources associated with photosynthesis and organic carbon burial exceed the sinks associated with volcanic gases, reduced mineral oxidation, and respiration. The Great Oxidation Event represents a long interval when the balance shifts in favor of net oxygen gain, in part because earlier sinks become saturated or less effective. For example, as most easily accessible ferrous iron in surface oceans and weathered rocks is oxidized and buried, the capacity of these reservoirs to quickly consume new oxygen declines. Similarly, changes in tectonic and volcanic regimes can adjust the flux of reduced gases to the atmosphere. Weathering of newly uplifted continental crust, especially if it contains large amounts of reduced sulfur and iron minerals, can briefly increase oxygen consumption, but over longer periods it also supplies sulfate and other oxidized species that support sulfate reduction and sulfide burial in the oceans. These coupled processes form a feedback system in which increased oxygen can lead to more oxidation of reduced materials and more burial of sulfides and organic carbon, which in turn can allow further oxygen accumulation. The combined redox budget of carbon, sulfur, and iron can be expressed in terms of how many equivalents of oxidizing or reducing power are stored or released when different minerals and organic compounds are formed or destroyed. For instance, when organic carbon and pyrite are buried together, significant reducing power is transferred to the crust, leaving the surface system more oxidizing. When these materials are later uplifted and weathered, the reverse can occur, consuming oxygen and releasing carbon dioxide and sulfate. Over the Proterozoic, the net direction of these fluxes appears to favor gradual oxidation, but the rate is not constant. Periods of relatively rapid change in isotopic compositions suggest intervals when burial or weathering of certain compounds accelerates or slows, perhaps due to changes in sea level basin geometry or biological productivity. These variations are superimposed on longer-term trends and can produce complex patterns in the rock record that require careful interpretation. The cycles of these elements are also linked to climate. For example, increased burial of organic carbon can draw down atmospheric carbon dioxide, potentially cooling the climate, while changes in silicate weathering rates can regulate carbon dioxide over millions of years. In turn, climate affects weathering and sedimentation. Warmer, wetter climates enhance chemical weathering, whereas colder or drier climates slow it. During glacial intervals, the exposure of fresh rock under ice and the grinding of material by glaciers can prepare large amounts of fine sediment that weathers quickly after ice retreats, temporarily increasing carbon dioxide uptake. The interplay between climate and geochemical cycles thus contributes to the timing and magnitude of glaciations and warm periods, including the long mid-Proterozoic intervals of moderate climate and the later Neoproterozoic Snowball Earth events. Throughout these processes, microscopic life is both a driver and a respondent. Photosynthetic microorganisms control large parts of the carbon and oxygen cycles, while bacteria and archaea that carry out sulfate reduction, methanogenesis, and other metabolisms shape the sulfur and carbon cycles in anoxic environments. Their collective activity adjusts the distribution of reduced and oxidized species in the oceans and sediments, and therefore the rates at which various minerals form and are buried. At the same time, the redox state of their environment constrains which metabolisms are possible and how energy can be harvested. The Proterozoic element cycles are therefore best understood as a tightly interconnected network in which physical, chemical, and biological processes operate together to reshape the surface Earth from a low oxygen, strongly reducing system toward a more oxidizing one, with each step recorded in the composition of rocks, the chemistry of the oceans, and the behavior of the atmosphere. The continents of the Proterozoic are not fixed blocks, but moving plates that collide, merge, and separate over hundreds of millions of years, and this slow motion creates a variety of sedimentary basins that store the products of weathering, erosion, and chemical precipitation. Early in the Eon, large cratonic cores that formed in the Archean support stable platforms where new sediments are laid down on older crystalline basement. As time passes, these platforms receive layers of sandstone shale, carbonate and iron-rich chemical deposits that together build thick sequences. The geometry and depth of each basin depend on the balance between subsidence, which creates accommodation space, and sediment supply, which fills that space. When subsidence outpaces sedimentation, deep basins with fine-grained sediments and potential for organic rich layers develop. When sediment supply is high, as during active mountain building and erosion, coarser materials spread widely across shallow shelves and lowlands. Supercontinental cycles are a characteristic feature of Proterozoic tectonics. At times, many continental fragments cluster into large land masses forming long interior plateaus and broad peripheral margins. When continents assemble, convergent plate boundaries and continental collisions generate mountain belts, orogens that rise over wide regions. These mountain ranges are sources of sediment feeding rivers that transport weathered material into adjacent foreland basins and onto continental shelves. As mountains erode, the composition of sediments can shift from feldspar and lithic-rich detritus close to the source to more quartz-rich sands and muds farther out. The erosion of uplifted terrains also exposes different rock types to chemical weathering, influencing the flux of ions such as calcium, magnesium, and sulfate to the oceans, and thereby affecting the chemistry of seawater and the rates of carbonate and sulfide mineral formation. When supercontinents begin to rift and separate, new passive margins form along the edges of the thinning crust. These margins often host wide continental shelves that descend gently from land to deeper water. In such settings, thick accumulations of shallow marine sediments can build up over tens or hundreds of millions of years. Carbonate platforms composed largely of limestones and dolostone are common on these shelves, especially in warm, clear, relatively shallow seas. The persistence of these platforms indicates extended intervals of relatively stable sea level and climate during which carbonate precipitation keeps pace with subsidence. Within these carbonate sequences, changes in texture, mineralogy, and fossil content record gradual adjustments in seawater chemistry and biological communities as oxygen slowly becomes more widespread in some parts of the ocean. In deeper parts of passive margin, basins and in interior seaways, fine-grained muds and silts settle from suspension to form shales and siltstones. In many Proterozoic basins, these mud rocks contain significant amounts of organic matter, preserved because bottom waters are often anoxic and sometimes sulfidic. The lack of oxygen at the seafloor slows decomposition and allows organic carbon to accumulate in sediments. Over time, these organic-rich layers become important sinks for reduced carbon and sulfur, and they record the interaction between basin geometry, ocean redox structure, and biological productivity. Variations in the thickness, extent, and geochemical character of these shales across different basins reflect regional differences in subsidence connection to the open ocean and nutrient supply from land. Rift-related basins within continents also develop during episodes of extension. These basins can be narrow and deep, bounded by steep faults that create accommodation space faster than sediments can fill it. In their early stages, lacustrine and fluvial deposits may dominate recording non-marine environments with variable hydrology. As rifts deepen and connect to the ocean, marine conditions can invade and thick sequences of mixed continental and marine sediments may form. Volcanic activity is often associated with rifting, adding layers of lava and ash to the stratigraphy and supplying fresh rock for weathering. These volcanic products contribute both to the physical architecture of basins and to the chemical fluxes that influence seawater composition. In active margin settings along subduction zones, volcanic arcs and accretionary prisms contribute additional complexity. Here, sediments derived from eroding arcs and from scraping oceanic sediments off the downgoing plate accumulate in forearc and trench basins. Turbidites, which are gravity-driven flows of mixed sand and mud, deposit characteristic graded beds that can stack into thick packages. These deposits testify to repeated episodes of slope instability and rapid sediment transfer from shallow to deep settings. They also move organic matter and reactive minerals into deeper parts of the basin where they can participate in redox reactions and be buried. The Proterozoic sedimentary record of such margins demonstrates that tectonic processes place many different environments side by side, each with its own conditions for sedimentation and diagenesis. Glacial deposits appear at several times within Proterozoic sequences and provide direct evidence for ice-related processes acting on the continents and in nearby seas. During early Proterozoic glaciations, such as those associated with the Huronian interval diamictites containing a mix of fine and coarse material striated clasts and facetted pebbles, are preserved in basins that later become part of stable cratons. These deposits may occur above and below other sedimentary units, indicating multiple glacial episodes separated by non-glacial conditions. The presence of glacial sediments at low paleolatitudes inferred from paleomagnetic data and the positions of continents at the time of deposition suggest that ice can extend far from the poles under certain climatic states. Later in the Proterozoic, other glacial units, in some cases overlain by distinctive carbonate layers, are preserved on several continents and contribute to reconstructions of more extreme glacial events. The stacking patterns of different sediment types in Proterozoic basins, often described as stratigraphic successions, reflect shifts in sea-level tectonic activity and environmental conditions. For example, a typical succession might begin with fluvial or deltic sandstones deposited during an early phase of basin subsidence grade upward into shallow marine carbonates laid down as the basin deepens and connects to the open ocean, and then transition to deeper water shales and turbidites as the basin continues to subside or as sediment supply patterns change. Interruptions by volcanic ash layers provide time markers that can be dated radiometrically, anchoring the relative sequences to numerical ages. In some cases, glacial diamictites or iron-rich chemical sediments punctuate these successions, marking intervals when climate or redox state departs significantly from background conditions. Diagenesis, the suite of physical and chemical changes that sediments undergo after deposition, and during burial further modifies Proterozoic rocks. Compaction under the weight of overlying layers reduces pore space and expels water. Cementation by minerals such as quartz calcite or iron oxides binds grains together. In some settings, fluids moving through sediments alter mineral assemblages, for instance converting aragonite to calcite or forming new clay minerals. Redox-sensitive elements such as iron, manganese and sulfur can be redistributed as conditions change during burial, producing features such as concretions, nodules and color banding. These later alterations must be considered when interpreting original depositional conditions, but they also contain information about the evolving chemical environment of basins as they pass from shallow to deep burial, and in some cases back toward the surface during uplift. Over the full span of the Proterozoic, the combined record of continental and marine sediments, glacial deposits, carbonates, shales, and iron, rich layers forms a three-dimensional archive of how continents move, how basins form and fill, and how climate and ocean chemistry influence what is preserved. This archive shows that tectonic processes continuously reshape the locations and types of environments available for sedimentation, that basins can capture long histories of stable conditions as well as brief episodes of marked change, and that the distribution of different rock types through time is closely connected to the broader evolution of oxygen climate and the state of the oceans. The continents and their basins thus act as both participants in and recorders of the Proterozoic transformations, hosting the interfaces where atmosphere, ocean, and lithosphere meet, and leaving behind the layered evidence on which reconstructions of this eon depend. Within the Proterozoic oceans and along their shallow margins, microscopic life forms create extensive communities that cover sediments, grow on carbonate platforms, and occupy many chemical niches. Cyanobacteria are widespread in the sunlit surface layers, forming dense mats on tidal flats, lagoon floors, and the tops of carbonate banks. These mats consist of layers of filamentous and coccoid cells embedded in sticky extracellular substances that trap fine sediment grains and bind them together. Over time, cycles of growth, sediment trapping, and mineral precipitation build laminated structures known as stromatolites, which grow upward as new microbial layers adjust to changes in water depth, sediment supply, and light. In cross-section, stromatolites often show fine repeated laminae that reflect small shifts in conditions such as variations in water, energy sediment influx, or microbial community structure. In the early Proterozoic, stromatolites are abundant and diverse, indicating that microbial mats are among the dominant builders of shallow marine structures, and that they play a major role in mediating carbonate precipitation and local geochemical cycles. The metabolism of cyanobacterial mats centers on oxygenic photosynthesis, which uses sunlight to split water and fix carbon dioxide into organic matter, releasing molecular oxygen as a byproduct. During daylight, photosynthesis in the upper layers of the mat can produce oxygen concentrations that exceed those in overlying waters, while in deeper layers, and at night, respiration and other processes consume oxygen and produce carbon dioxide. This vertical gradient means that different depths within a single mat experience different redox conditions over daily and longer cycles. Near the surface, conditions can be oxidizing during the day, supporting organisms that tolerate or require oxygen, while deeper layers remain anoxic much of the time, and host microorganisms that use alternative electron acceptors, such as sulfate, or that perform methanogenesis, the production of methane from carbon compounds. In this way, a stratified microbial mat resembles in miniature the vertical redox structure of the larger Proterozoic ocean, with oxidized and reduced zones stacked over one another and linked by diffusion and metabolic fluxes. As the Proterozoic progresses, early eukaryotic cells appear and begin to share these habitats with bacterial and archaeal communities. Eukaryotes are characterized by internal structures such as a nucleus and organelles, including mitochondria that carry out aerobic respiration. The origin of eukaryotes likely involves endosymbiotic events, in which one cell incorporates another as a stable internal partner, but the detailed sequence and timing of these events remain topics of active research. Fossil and molecular evidence suggest that some eukaryotic lineages are present by the mid-Proterozoic, although their diversity and ecological roles may initially be limited compared with later times. In the oceans, early eukaryotes may take the form of single-celled plankton, small algae, and simple multicellular forms that live in association with microbial mats in the water column or within sediments. These eukaryotes participate in the cycling of carbon, nutrients, and redox-sensitive elements by performing photosynthesis, grazing on bacteria, and decomposing organic matter. The presence of mitochondria in many eukaryotes allows them to use oxygen efficiently when it is available, giving them access to energy-rich pathways of aerobic respiration, but it also means that they are sensitive to the spatial and temporal distribution of oxygen in their environment. In strongly stratified Proterozoic oceans where oxygenated surface waters overlie, anoxic deeper layers, eukaryotes that rely heavily on oxygen, are likely confined to regions where oxygen penetrates, such as near the surface in well-ventilated shelves, and in local settings where mixing brings oxygen downward. Microfossils from Proterozoic sediments include a variety of forms attributed to eukaryotic algae and other protists. Some show ornamented cell walls or complex shapes that distinguish them from simpler bacterial cells. These microfossils appear in sequences that also record changes in carbon and sulfur cycles, and in ocean redox structure, suggesting that eukaryotic diversification may be linked to shifts in nutrient availability, oxygen distribution, and the structure of microbial ecosystems. For example, an increase in phosphorus or other limiting nutrients in certain basins can support higher primary productivity, which in turn increases the flux of organic matter to depth and influences redox conditions. Eukaryotic algae may take advantage of such nutrient-rich conditions in the photic zone, while heterotrophic eukaryotes graze on bacteria and algae, forming simple food webs within the microbial realm. These interactions do not yet produce the complex macroscopic ecosystems seen later in the Phanerozoic, but they represent an important step toward greater ecological structuring. On shallow shelves and in restricted basins, microbial mats continue to dominate many benthic environments, even as eukaryotes spread. The mats can exclude or limit the settlement of larger organisms by forming continuous cohesive layers on the sediment surface. At the same time, microscale heterogeneity within the mats, such as small ridges, pits, and channels, provides a variety of microhabitats for different microbial taxa. Early eukaryotes may live on or within these mats, feeding on bacteria or dissolved organic substances, or forming symbiotic relationships that influence mat structure and function. In some cases, eukaryotic algae may contribute directly to carbonate precipitation by altering the chemistry of pore waters through photosynthesis and respiration, further integrating into the existing microbial frameworks that build stromatolites and other microbialites. In deeper waters and in the water column away from coasts, free-living planktonic microorganisms, both prokaryotic and eukaryotic, occupy the photic zone and underlying layers. Cyanobacteria and other photosynthetic cells capture light and form the base of pelagic food webs, while heterotrophic bacteria and small eukaryotes remineralize organic matter as it sinks. The balance between production and decomposition in these settings controls the flux of carbon and nutrients to the deep ocean, and influences the position of redox boundaries. For example, high export of organic matter can draw down oxygen in subsurface waters through respiration, pushing the anoxic zone upward and expanding regions where sulfate reduction, methanogenesis, and other anaerobic processes dominate. The distribution of microscopic life thus feeds back into the larger-scale redox structure of the oceans and indirectly into the burial of organic carbon and sulfides that affects atmospheric oxygen over long timescales. During the long mid-Proterozoic interval of relatively stable climates and ocean structures, microbial communities have extended periods to adapt to prevailing conditions. This stability may allow for gradual diversification of eukaryotic groups in both benthic and planktonic environments, although the fossil record remains sparse and biased toward organisms with more robust cell walls, or those that inhabit depositional settings conducive to preservation. Molecular clock estimates based on living lineages suggest that many major eukaryotic clades originate during this time, possibly including ancestors of green algae, red algae, and other groups that will later contribute to more complex ecosystems. However, the visible effects of this diversification on the sedimentary record remain subtle compared with the more prominent signatures of microbial mats and inorganic chemical processes. Oxygen, while more abundant than in the Archean, is still unevenly distributed, and large expanses of the deep ocean remain anoxic and ferruginous or sulfidic. As a result, many microorganisms continue to rely on metabolisms that do not require oxygen, such as anoxygenic photosynthesis, sulfate reduction, and methanogenesis. These metabolisms interact with those of oxygen-producing and oxygen-consuming organisms to sculpt the chemical gradients in sediments and water columns. In sediments below microbial mats, for instance, a vertical succession of metabolic zones may be present with oxygen respiration near the surface, giving way to nitrate reduction, manganese and iron reduction, sulfate reduction, and finally, methanogenesis at depth. The thickness and position of each zone reflect the supply of electron donors and acceptors and the rates of diffusion and advection, and they can adjust as environmental conditions change. This layered biological structure mirrors and helps to maintain the broader chemical layering of the Proterozoic oceans. In summary, Proterozoic microscopic life is organized into extensive microbial mats on the seafloor, free-living plankton in the water column, and subsurface communities in sediments with cyanobacteria and other bacteria, forming the bulk of biomass and early eukaryotes gradually increasing in diversity and ecological significance. These communities collectively mediate the exchange of carbon, oxygen, sulfur, and other elements between the atmosphere, oceans, and sediments. They respond to the chemical and physical structure of their environment, yet they also modify that structure through their metabolisms. The rise of oxygen, the presence of stratified redox layers in the oceans, and the appearance of more complex cells are therefore closely linked, each influencing the others within the Proterozoic biosphere, and setting the inner biological context in which later climatic and geochemical events, including the Snowball Earth episodes, will unfold. In the later part of the Proterozoic, the surface climate begins to shift from the long intervals of relative stability that characterized the mid-eon towards states that are cooler and more variable on geological timescales. The basic external conditions remain unchanged in their essentials. The Sun continues its slow, steady, brightening orbital cycles, proceed with regular rhythms, and the distribution of solar energy between latitudes follows the same geometric rules. The emerging differences arise from internal processes within the Earth system, particularly those that affect atmospheric greenhouse gas levels, surface reflectivity, and the arrangement of continents and oceans. Together, these processes gradually alter the energy balance at the top of the atmosphere and the way that energy is stored and redistributed at the surface. As time moves toward the Neo-Proterozoic continental positions, change as plate motions assemble large land masses into new configurations. Many reconstructions place substantial continental areas in low and mid-latitudes where solar input is relatively high. When large continents sit near the equator, their surfaces receive strong direct sunlight and can support intense weathering in warm, wet climates, especially where mountains and highlands provide relief and rainfall is sustained. Chemical weathering of silicate rocks under these conditions consumes carbon dioxide from the atmosphere, as carbonic acid reacts with minerals forming dissolved ions that are carried to the oceans. Over millions of years, an increase in low-latitude continental area and uplift can therefore enhance the global rate of silicate weathering, drawing down atmospheric carbon dioxide and weakening the greenhouse effect. This long-term reduction in carbon dioxide occurs in a delicately balanced system. Volcanic and metamorphic processes continue to release carbon dioxide, and the weathering sink adjusts as climate cools and as fresh rock is exposed or buried. In warmer climates, weathering is more vigorous and consumes more carbon dioxide, tending to cool the planet. As the climate cools and weathering slows, volcanic sources can gradually rebuild carbon dioxide levels, tending to warm the planet. This feedback helps stabilize climate over long times, but when boundary conditions change, such as through major rearrangements of continents, the balance can be shifted for extended intervals. In the late Proterozoic, a combination of enhanced weathering, evolving biological activity, and changes in sea level and basin configuration appears to favor lower background carbon dioxide levels than in some earlier times, making the climate system more susceptible to cooling when other factors push in that direction. The distribution and extent of ice and snow respond to these slow shifts in greenhouse gas concentrations. As mean global temperatures decline, polar regions and high-altitude areas build more persistent snow cover and glaciers. The growth of ice sheets increases the reflectivity of the surface, meaning that a greater fraction of incoming solar radiation is reflected back to space rather than absorbed. This change in albedo leads to further cooling, reinforcing the initial temperature decline. Even modest expansions of ice cover into lower latitudes can amplify this feedback, particularly if sea ice spreads across previously open ocean, replacing dark water surfaces with bright ice. During the Neo-Proterozoic, geological evidence indicates that glaciations become more extensive and in some intervals reach much lower latitudes than in the long mid-Proterozoic. The atmosphere during this time carries a composition that differs from earlier phases in ways that affect climate sensitivity. Oxygen is present at low but appreciable concentrations. Methane is generally maintained at lower levels than in the Archean, and earliest Proterozoic, and carbon dioxide is subject to the long-term drawdown associated with weathering and organic carbon burial. With methane suppressed in a more oxidizing atmosphere, the climate system cannot rely on high methane concentrations to provide strong greenhouse warming. Instead, carbon dioxide is the primary long-lived greenhouse gas, and its concentration becomes key control on whether the planet leans toward warmer or cooler mean states. If carbon dioxide is reduced below certain thresholds by prolonged weathering, organic carbon burial, and limited volcanic replenishment, the planet's capacity to retain heat declines to the point where ice can accumulate even at lower latitudes under the same solar input. Ocean circulation continues to transport heat from low to high latitudes, but the pattern and strength of that circulation respond to changing surface temperatures and salinity contrasts. As climates cool and sea ice expands, polar surface waters become fresher due to freezing and meltwater input, and the formation of very cold, salty deep waters can be affected. In some cases, denser waters may still sink and drive overturning sustaining heat transport from low latitudes into polar regions and moderating cooling. In other cases, if surface stratification strengthens due to cold, fresh layers overlying warmer, saltier water, deep water formation can weaken, reducing the efficiency of heat redistribution. These changes influence how quickly cooling in high latitudes can spread and how long cold conditions can be maintained once established. The presence or absence of sea ice in different regions also affects exchanges of heat and moisture between atmosphere and ocean. On continents, the growth of mountain belts and high plateaus in the Proterozoic contributes to regional climatic changes that feed into the global picture. Uplifted terrains intercept moist air masses and enhance precipitation on windward slopes, increasing chemical weathering and erosion. The resulting sediments deliver nutrients such as phosphorus and iron to the oceans, which can influence primary productivity and the burial of organic matter. If burial of organic carbon increases in certain periods and regions, more oxygen can accumulate in the atmosphere and oceans, while carbon dioxide is drawn down. This combination can further cool the climate and change the redox structure of the oceans, reinforcing the trend toward more oxidizing surface conditions and cooler temperatures. At the same time, the erosion of these elevated regions eventually lowers relief and can reduce weathering rates, allowing carbon dioxide to rebuild. The interplay between tectonic uplift, weathering sediment supply and climate thus remains an active part of the late Proterozoic climate system. Sea level variations driven by changes in ocean basin volume and by the presence or absence of large ice masses modify the area of continental shelves and shallow seas. When sea levels are high, extensive shallow marine environments support widespread carbonate deposition and microbial communities that influence local and global geochemical cycles. When sea levels fall, shelves may be exposed or reduced, altering the sites where carbonates and organic-rich sediments accumulate. These shifts affect the long-term carbon cycle and can change the rates at which carbon dioxide is removed from or returned to the atmosphere. Throughout the late Proterozoic, the planet experiences repeated glacial and interglacial intervals, superimposed on the longer-term cooling trend. Orbital cycles continue to modulate the distribution of solar energy between seasons and latitudes, and these cycles can pace the advance and retreat of ice sheets when the climate is near thresholds for glaciation. In cooler background states, small changes in insolation due to orbital variations can have outsized effects on where and when snow persists through summers, allowing ice sheets to grow or shrink. In warmer background states, the same orbital variations may have smaller impacts. As the late Proterozoic progresses, the combination of low greenhouse gas levels, favorable continental positions, and feedbacks involving ice and albedo increasingly favor conditions where ice can expand over wide areas for long times. The atmospheric and oceanic redox structure continues to evolve during this period, but the changes remain within bounds that allow both oxygen-dependent and anaerobic metabolisms to operate. Oxygenated surface waters and atmosphere coexist with anoxic and ferruginous or sulfidic deep waters in many basins, maintaining sharp redox gradients. The distribution of these gradients affects how nutrients are cycled and how much organic matter is buried, which in turn influences carbon dioxide and oxygen levels and feeds back on climate. In some intervals, expanded anoxia in mid-depth or deep waters can reduce nutrient return to the surface, moderating productivity and organic burial, while in others improved ventilation can enhance oxygenation of deeper waters and alter the balance of microbial processes. These variations introduce additional complexity into the coupling between climate-ocean chemistry and biology, but the broad direction in the late Proterozoic remains one of a system moving toward cooler, more ice-prone states. The geological record from this time captures evidence for these shifts in the form of more frequent and extensive glacial deposits, changes in carbonate deposition patterns and variations in the isotopic composition of carbon and other elements. Sequences of sediments show transitions from non-glacial to glacial facies, and back again sometimes with sharp boundaries that indicate rapid environmental change, at least in geological terms. At the same time, many successions preserve thick intervals of relatively uniform sediments, suggesting that even within a cooling trend, regions of the planet experience long periods of stable, moderate conditions. The coexistence of these signals reflects the heterogeneous nature of Earth's climate and environments, where different regions can follow different trajectories under the same global forcing. Overall, the steps toward Neoproterozoic cooling can be understood as the cumulative result of small imbalances in the carbon cycle. The evolving arrangement of continents and mountains, the sensitivity of ice and snow to temperature and insolation, and the feedbacks that link climate to weathering and sedimentation. By the time that the planet enters the later Neoproterozoic, these processes have positioned the Earth system close to states in which ice can expand very widely under the existing solar input, and in which the climate becomes capable of sustaining glaciations that are more extensive and persistent than most earlier Proterozoic events, within the same framework of physical laws and boundary conditions that have governed the planet since the Eon began. During the Cryogenian period in the late Proterozoic, the climate system enters states in which ice sheets and sea ice expand far beyond the ranges seen in most earlier intervals, possibly reaching into low latitudes and covering a large fraction of the planet's surface. Geological evidence from multiple continents, including glacial deposits that appear to have formed near ancient equatorial regions, supports the view that at least some cryogenian glaciations are unusually extensive. At the planetary scale, these events can be described as near-global glaciations, and some models and interpretations suggest that oceans may be covered by continuous or almost continuous ice, with only limited regions of open water, if any. The exact extent and uniformity of ice cover remain subjects of study, but the main point is that these glaciations involve an Earth that is significantly more reflective and more ice-covered than during typical ice ages. The entry into a cryogenian glaciated state can be understood in terms of the same radiative balance and feedback mechanisms that shaped earlier Proterozoic climates, but operating under boundary conditions that favour stronger cooling. If background carbon dioxide levels are already relatively low due to enhanced silicate weathering on low-latitude continents and effective burial of organic carbon, the greenhouse effect is weakened. Under these conditions, a modest additional reduction in greenhouse gases, a small decrease in solar absorption at the surface, or a combination of both can be enough to allow snow and ice to persist at lower latitudes through summer. As snow and ice extend equatorward, they increase the mean albedo of the planet, reflecting a larger share of incoming solar radiation back to space. This reduces the amount of energy available to heat the surface and lower atmosphere, driving further cooling and further expansion of ice. This positive feedback between ice cover and temperature is known as the ice albedo feedback. Once ice lines move sufficiently close to the equator where solar radiation is normally strongest, the feedback becomes especially effective because bright ice surfaces replace dark ocean or land in regions that previously absorbed large amounts of sunlight. Climate models indicate that beyond a certain threshold position of the ice margin, the combined effect of reduced greenhouse gases and expanded reflective surfaces can push the system toward a stable equilibrium in which sea ice covers nearly the entire ocean and continental ice sheets extend across most land areas. In such a state, seasonal cycles continue, but even in summer, sunlight is often insufficient to melt the thick ice cover at low and mid-latitudes, and only limited marginal or coastal melting occurs. The atmosphere above an ice-covered planet retains its structure of troposphere and stratosphere, but its interaction with the surface is altered. Over extensive ice sheets and sea ice, sensible and latent heat fluxes between surface and air are reduced compared with open water or vegetated land. This limits the capacity of the surface to warm the lower atmosphere and to supply moisture for clouds and precipitation. In many regions, precipitation rates may decline, and much of the interior of large ice sheets could remain cold and dry, gaining mass mainly along their margins. However, coastal and equatorial zones influenced by residual oceanic heat and topography can still support storm systems that bring snowfall, helping to maintain and thicken ice. Winds continue to respond to temperature gradients between equator and poles, but these gradients are modified in magnitude and position by the presence of extensive ice. The hydrological cycle over land and sea is therefore reorganized with altered patterns of snow accumulation and sublimation. Despite the dominance of ice at the surface, the interior of the planet and the deep parts of the ocean continue to supply heat. Geothermal heat flux from Earth's interior and heat release from hydrothermal systems at mid-ocean ridges and volcanic centers provide a persistent upward energy flow. In a near-globally glaciated state, this heat must pass through thick sea ice and continental ice before it can be radiated to space. Some of it warms the base of ice sheets and the uppermost ocean beneath sea ice, potentially producing basal melting or maintaining thin layers of liquid water at interfaces. In the oceans, this internal heating, combined with slow mixing and any remaining salinity contrasts, can sustain circulation beneath the ice cover, although at reduced rates compared with an ice-free surface. This internal movement of heat and water masses is important for understanding how a Snowball Earth state can persist for long intervals without the ocean freezing solid to the sea floor. The persistence of cryogenian glaciations over millions of years implies that the overall energy balance of the planet remains in favor of cold conditions for extended periods. At the same time, Earth's tectonic and volcanic processes do not stop during these intervals. Volcanic degassing continues to inject carbon dioxide and other gases into the atmosphere. Under non-glacial conditions, a significant part of this carbon dioxide would be removed by silicate weathering on exposed continents and by carbonate formation in shallow seas. During near-global glaciation, however, much of the continental surface is shielded by ice, and areas of active chemical weathering are reduced. Rivers that would normally carry weathering products to the ocean are less effective or absent in many regions. This reduction in the efficiency of the carbon dioxide sink allows volcanic emissions to accumulate in the atmosphere over time. The gradual build-up of carbon dioxide strengthens the greenhouse effect, increasing the downward long-wavelength radiation that reaches the ice-covered surface. In parallel, other processes may contribute to changes in the surface energy balance. The deposition of volcanic ash or dust on ice surfaces can locally darken them, reducing albedo, and allowing more sunlight to be absorbed where the impurities accumulate. Changes in cloud properties and distribution in response to altered moisture and aerosol sources can also influence how much solar energy reaches the surface and how effectively long-wavelength radiation escapes to space. The relative importance of these contributions remains uncertain, and different models explore different combinations of mechanisms. However, the general concept is that while the ice albedo feedback helps to maintain cold conditions once they're established, the slow but continuous input of greenhouse gases from Earth's interior gradually moves the climate system toward a new balance. When atmospheric carbon dioxide concentrations rise high enough, the increased greenhouse warming can offset the high albedo of the ice-covered surface. At that point, in some regions and seasons, surface temperatures can begin to climb above freezing more consistently, leading to enhanced melting of sea ice and the margins of continental ice sheets. As melt ponds and open water patches develop, they absorb more solar radiation than the surrounding ice, further warming local environments and promoting additional melting. This initiates a reversal of the ice albedo feedback. Diminishing ice cover reduces planetary reflectivity and allows more energy to be retained, which accelerates deglaciation. The transition out of a Snowball Earth state may therefore proceed relatively rapidly in geological terms once greenhouse gas levels and seasonal insolation patterns support persistent melting at low and mid-latitudes. The rock record of cryogenian glaciations includes not only deposits that indicate the presence of ice, such as diamictites and striated surfaces, but also overlying layers of carbonate rocks that rest directly on glacial sediments in some regions. These so-called cap carbonates are interpreted as having formed shortly after the end of major glacial episodes in oceans that may have experienced high concentrations of dissolved inorganic carbon and rapid changes in chemistry as ice retreated and weathering and carbonate precipitation resumed. The details of how these carbonates form and what they imply about post-glacial conditions are still debated, but their widespread and distinctive nature highlights the contrast between the glacial and post-glacial states. Together, glacial deposits and associated carbonates provide physical evidence that the climate system can move from warm or moderate conditions into extreme ice-covered states, and then back to more temperate conditions within the late Proterozoic. Across the span of the cryogenian, multiple glaciations occur separated by intervals when ice retreats, and more open ocean and ice-free land reappear. Each glacial cycle reflects a particular balance between greenhouse gas levels, surface reflectivity, ocean circulation, and internal heat modulated by tectonic and volcanic influences. The concept of Snowball Earth summarizes the most extreme of these states in which near global ice cover and strong ice albedo feedback dominate the climate, while eventual recovery relies on the long-term accumulation of greenhouse gases and the fundamental tendency of the Earth system to move toward radiative equilibrium under changing boundary conditions. In this way, cryogenian glaciations represent an expression of the same physical principles that govern earlier and later climates, but driven to more extreme outcomes by the particular configuration of the late Proterozoic Earth. During near-global glaciations of the cryogenian, the oceans remain liquid beneath thick sea ice, and beneath the margins of continental ice sheets, forming a hidden but active part of the climate and geochemical system. The ice cover at the surface acts as a barrier that reduces direct contact between the atmosphere and seawater, weakening exchanges of gases, heat, and moisture. However, it does not completely isolate the ocean. Cracks leads polyneas and regions of thinner ice can persist near coasts above zones of upwelling, or where winds and currents deform the ice. In addition, the base of the sea ice interacts continuously with the underlying water through freezing, melting, and brine rejection. When sea ice forms, pure water freezes and salt is concentrated in brine that drains downward into the ocean, increasing the salinity and density of waters near the seafloor in some regions. When ice melts, it releases relatively fresh water that can form a less dense surface layer when it reaches the ocean below. These processes create vertical and horizontal gradients in temperature and salinity, even under a largely ice-covered surface. Within this environment, ocean circulation persists, driven by density contrast geothermal heating from below and any remaining wind stress that can be transmitted through the ice. In some models of cryogenian oceans, the circulation takes the form of slow overturning cells in which cold, dense waters sink in high latitude or high salinity regions, and warmer, slightly less dense waters rise elsewhere. Hydrothermal systems at mid-ocean, ridges and seamounts inject heated, chemically distinct fluids into the deep ocean, adding reduced metals such as iron and manganese, as well as other elements to seawater. These hydrothermal plumes rise until they reach water layers of similar density, then spread laterally, transporting heat and dissolved substances across ocean basins. The combination of basal heat input and hydrothermal activity helps maintain temperature gradients and prevents the entire water column from coolly homogenizing even during long glacial intervals. The chemistry of cryogenian seawater under ice reflects both continuity and change relative to earlier Proterozoic conditions. The deep ocean likely remains largely anoxic and in many regions ferruginous, with high concentrations of dissolved ferrous iron, sourced from hydrothermal vents and reduced sediments. The overlying waters, especially those that occasionally communicate with the atmosphere or with marginal open water, can carry more oxygen, creating a familiar pattern of oxidized surface layers over reduced deep layers. However, the reduced area and frequency of direct air-sea gas exchange under continuous ice cover can limit the supply of atmospheric oxygen to surface waters. As a result, the depth of oxygen penetration and the position of redox boundaries in the ocean may shift compared with the less glaciated times, with possible expansion of anoxic and ferruginous zones. At the same time, the reduced supply of fresh weathering products from continents during near global glaciation, especially sulfate and other ions produced by chemical weathering, can alter the balance of major ions and nutrients in the ocean. Rivers are less effective pathways for delivering dissolved and particulate material to the sea when large parts of the land surface are covered by ice, and when precipitation is low over interior ice sheets. Instead, subglacial meltwater carries finely ground rock flour and some dissolved ions to coastal zones and to sub-ice shelf cavities. These inputs can be locally significant, delivering both nutrients that can support productivity in marginal open water regions, and detrital material that influences sedimentation beneath and beyond the ice margins. Enclosed or semi-enclosed basins reduced connectivity with the open ocean and restricted circulation under ice can lead to distinctive chemical conditions with strong stratification and pronounced redox gradients. Sedimentation during cryogenian glaciations records these oceanic conditions in the form of fine-grained muds, dropstone bearing layers and intervals rich in iron and manganese minerals. Beneath floating ice shelves and sea ice particles released from the ice, including entrained debris from the continents, settle to the seafloor, forming diamictites and related deposits. In deeper parts of basins, slow settling of fine particles derived from glacial erosion, aeolian transport and limited biological production builds thick, relatively uniform mudstone sequences, where hydrothermal or upwelling fluxes bring iron-rich waters into contact with more oxidizing conditions. Iron oxides and hydroxides can precipitate, forming layers or nodules within the sediment. The interplay between iron-rich deep waters, oxygenated under ice surface waters, and the rate of organic matter supply determines whether ferruginous or sulfidic conditions develop at the seafloor. If sulfate supply from weathering and seawater remains limited, and if organic matter flux is modest, ferruginous anoxia may persist in many deep basin settings. The vertical structure of the cryogenian ocean under ice therefore likely ranges from cold, relatively fresh surface layers close to the ice base through thermocline and halocline zones, where temperature and salinity change with depth, to deeper, warmer and saltier waters influenced by geothermal heating and hydrothermal inputs. In regions of active basal melting at the underside of ice shelves, buoyant plumes of slightly fresher water can rise and flow outward, while in regions of strong brine rejection, during freezing dense saline waters can sink and spread along the seafloor. These circulation patterns can create pathways that connect subglacial cavities, continental margins and open ocean basins, allowing heat and dissolved substances to move between them even in the absence of extensive open water at the surface. Such circulation also influences the distribution of any biological communities that inhabit the ocean beneath the ice, because it controls where nutrients, redox interfaces and temperature conditions suitable for particular metabolisms occur. Over the duration of a cryogenian glaciation, slow but cumulative changes in ocean chemistry and structure occur as volcanic gases continue to enter the atmosphere-ocean system, as limited weathering and sedimentation proceed, and as hydrothermal activity persists. Dissolved inorganic carbon can accumulate in seawater as atmospheric carbon dioxide builds up and exchanges across limited open water and through thin or fractured ice. Changes in alkalinity, calcium and magnesium concentrations, and the saturation state with respect to carbonate minerals can all take place in this under-ice setting, preparing the conditions for rapid carbonate precipitation once deglaciation begins and broader air-sea exchange resumes. In this way, the cryogenian oceans beneath thick ice are not static reservoirs, but slowly evolving systems that integrate inputs from the interior from the ice-covered continents, and from the atmosphere above, maintaining layered redox structures and circulation patterns that set the scene for both the survival of life during glaciations and the geochemical responses that follow their end. The hidden ocean thus remains a central component of the late Proterozoic Earth system, even when its surface expression is largely obscured by ice at the scale of the planet. During extensive cryogenian glaciations, when ice sheets and sea ice cover much of the surface, life does not disappear, but persists in environments that remain physically and chemically suitable within the broader frozen setting. These environments, often described as refuges, are places where liquid water energy sources and necessary chemical gradients are present, despite low temperatures and widespread ice. The exact distribution and structure of these refuges cannot be reconstructed in complete detail, but a combination of physical reasoning, modern analogues, and geochemical evidence supports the view that microscopic organisms, including cyanobacteria, other bacteria and archaea, and early eukaryotes continue to inhabit selected niches in the ocean, at ice interfaces and within subglacial and coastal environments. One class of potential refugees lies near the interface between sea ice and the ocean. Even when sea ice is thick and extensive, its base is often irregular and porous at small scales, forming a network of channels and pockets filled with concentrated brine. As sea ice forms, salt is rejected from the growing ice lattice and accumulates in thin films and cavities, producing brines that are colder and more saline than the underlying seawater. These brine channels can host gradients in temperature, salinity, and chemical composition over very short distances, and in modern polar seas they support microbial communities adapted to cold saline conditions. By analogy, during cryogeny and glaciations, brine channels and the thin liquid layers at the ice-ocean interface likely provide habitats for microorganisms that tolerate low temperatures and high salinities. In these microenvironments, diffusion and slow circulation bring in nutrients and remove waste products, while small amounts of light transmitted through snow and ice, especially in lower latitudes or thinner regions, can support limited photosynthesis by cyanobacteria or eukaryotic algae. The thickness and optical properties of cryogeny and sea ice are subjects of ongoing study, and proposed thicknesses range from tens to possibly hundreds of meters in some models. Even under thick ice fractures, pressure ridges, leads and polyneas can occur, especially near coasts and along zones of differential motion. Leads are linear openings in sea ice created by winds and currents, while polyneas are larger, more persistent areas of open water or thin ice maintained by the combined effects of winds, currents, and upwelling warmer water. In a near globally glaciated ocean, such features may be less widespread than in modern polar regions, but they are unlikely to be completely absent. Where they exist, they provide direct contact between atmosphere and ocean, allowing gas exchange, episodic light penetration, and local primary production. Microbial communities concentrated in and around these openings can take advantage of intermittent light and nutrient inputs, producing organic matter that then spreads outward under the ice and supports heterotrophic metabolisms over wider areas. Another set of refugees is associated with the margins and bases of continental ice sheets. Beneath thick ice, geothermal heat from Earth's interior and frictional heating from ice movement can produce basal melting, forming thin films or thicker pools of liquid water at the ice bed interface. These subglacial environments are shielded from direct contact with the atmosphere and may have limited connections to the ocean, but they can host their own hydrological systems, with networks of channels, lakes and streams that drain toward ice margins or into subglacial cavities connected to the sea. Water in these systems interacts with rock and sediment beneath the ice, dissolving and transporting ions and fine particles. Chemical gradients develop between oxidized species supplied by occasional oxygen-bearing waters and reduced minerals and gases present in the bedrock and sediments. Microorganisms in such settings can exploit these gradients through chemolithoautotrophy, a mode of metabolism in which energy is obtained from inorganic redox reactions, instead of light, for example by oxidizing ferrous iron sulfide or hydrogen, and reducing electron acceptors such as sulfate or carbon dioxide. In this way, subglacial systems may sustain microbial life even in the absence of strong primary production from photosynthesis. At ice sheet margins where grounded ice meets the ocean, subglacial meltwater plumes can emerge at grounding lines and mix with seawater beneath floating ice shelves. These mixing zones host steep gradients in temperature, salinity, and chemical composition over small distances as fresh sediment-laden meltwater entrains seawater and rises along the ice base. Microbial communities can develop in these transition regions where they encounter both glacially derived nutrients and reduced compounds from subglacial weathering, as well as more oxidized seawater constituents. Sediment plumes deposit fine material on the seafloor, forming substrates that may host benthic microbial mats adapted to low light or darkness, depending on the thickness and optical properties of the overlying ice. Thermal anomalies associated with geothermal and hydrothermal activity provide additional refuges. Mid-ocean ridges, volcanic seamounts, and regions of enhanced heat flow continue to operate during cryogenian glaciations and release hot chemically reduced fluids into the deep ocean. Hydrothermal vents in these settings discharge mixtures of metal, sulfide, and other reduced species into cold oxygen, pore waters creating plumes and local environments with strong chemical disequilibria. Microorganisms can use these disequilibria as energy sources performing chemosynthesis to fix carbon into organic matter. Modern hydrothermal ecosystems demonstrate that rich microbial communities, including both bacteria and archaea, can thrive where light is absent but redox gradients are strong. In the cryogenian ocean, similar communities likely persist at hydrothermal sites independent of surface ice cover and provide continuous though spatially restricted sources of organic carbon and biomass. In addition to marine and subglacial refuges, some refuges may exist in terrestrial or marginal environments that are only intermittently covered by ice, or that experience local conditions allowing liquid water. Coastal mountain ranges, rift valleys or regions with strong geothermal gradients can contain ice-free rock faces, ephemeral meltwater streams or shallow pools during warmer seasons, even within a generally glaciated landscape. Microorganisms colonizing rock surfaces, soil-like materials, or thin films of water can form communities similar to microbial crusts and endolithic communities seen in modern cold deserts and high-latitude regions. Cracks and pores within rocks provide protection from extreme temperature fluctuations and radiation, and they can hold small amounts of water for extended periods. While such habitats are likely limited in area compared with the global ice cover, they add to the diversity of environments where life can persist. Within marine refuges, the composition of the biota remains largely microscopic. Cyanobacteria, other photosynthetic bacteria, and small eukaryotic algae carry out primary production, where light reaches shallow sub-ice waters or ice-associated microenvironments. Heterotrophic bacteria and early eukaryotes consume organic matter, decomposing it and recycling nutrients. In deeper dark environments such as hydrothermal zones, subglacial lakes, and anoxic basins, chemotrophic bacteria and archaea perform metabolisms based on sulfur, iron, hydrogen, and other reduced compounds. Eukaryotic microorganisms that can tolerate low oxygen or exploit oxic-anoxic interfaces may be present near redox boundaries and in transitional zones where oxygen occasionally penetrates. The overall biomass and productivity of these systems during Snowball Earth intervals are uncertain and depend on factors such as nutrient supply, light availability, and the extent of habitable interfaces, but they are sufficient to maintain continuity of microbial lineages across glacial episodes. Some cryogenian and immediately post-cryogenian sedimentary rocks contain geochemical signatures interpreted as evidence for biological activity during and between glacial intervals, including organic carbon of biological origin and isotopic patterns consistent with ongoing cycling of carbon, sulfur, and other elements. Fossils of certain acritarchs, a term for organic walled microfossils and possible remains of simple multicellular organisms, indicate that eukaryotic lineages exist before, during, and after the cryogenian. The survival of these lineages implies that refuges provide environments where early eukaryotes can persist through the most severe glacial episodes, even if their geographic range and ecological roles are constrained. The structure and stability of these refuges are influenced by the same processes that govern the larger-scale ocean and climate. Changes in ice thickness, ocean circulation beneath the ice, volcanic and hydrothermal activity and atmospheric composition can expand or contract habitable zones in space and time. For example, an increase in volcanic outgassing may locally warm subglacial environments, or alter the chemistry of hydrothermal fluids, affecting the types of metabolisms that are favoured. Changes in circulation under the ice can modify the distribution of nutrients and redox interfaces redistributing communities that depend on them. Despite these variations, the robustness of microbial life to wide ranges of temperature, salinity, and chemical conditions, as evidenced by modern analogues in polar and subglacial environments, supports the view that Proterozoic microorganisms can adapt to the slowly changing conditions of a snowball Earth. Overall biological refuges during cryogenian glaciations can be described as a network of cold but habitable spaces embedded within a planet dominated by ice. These spaces include brine channels and ice bases in the ocean, subglacial hydrological systems beneath continental ice, hydrothermal and geothermal sites, margins of ice sheets, and limited coastal or terrestrial microhabitats. In each microscopic life relies on the presence of liquid water energy sources from light or chemical disequilibria and access to essential nutrients. The continuity of these conditions over millions of years allows microbial ecosystems to endure through extended glaciations, maintaining the cycles of carbon, sulfur, and other elements, and preserving the biological component of the Proterozoic Earth system until more temperate conditions return. As cryogenian glaciations end in the late Proterozoic, the climate system, oceans, and biosphere move into recovery states that differ from both the preceding Snowball Earth conditions and the earlier mid-Proterozoic regimes. Deglaciation begins when long-term volcanic degassing has raised atmospheric carbon dioxide to levels high enough that greenhouse warming can overcome the high albedo of extensive ice cover. Once melting starts at low and mid-latitudes, new areas of dark ocean and land are exposed, absorbing more solar radiation and accelerating warming. Ice retreats from continental margins and ocean surfaces first seasonally and then more permanently, and over time large ice sheets shrink back toward higher latitudes and elevations. The hydrological cycle strengthens as open water expands, with evaporation from newly ice-free seas feeding clouds, and precipitation over continents and oceans. Rivers and streams that were greatly reduced or redirected beneath ice sheets regain or establish surface courses delivering meltwater and renewed weathering products to the oceans. On the continents, glacial erosion has left behind freshly ground rock surfaces and thick layers of fine debris. As temperatures rise and liquid water becomes more widespread, chemical weathering intensifies on these young surfaces. Carbon dioxide from the atmosphere dissolves in rainwater and pore waters, forming weak acids that react with minerals in glacial sediments and exposed bedrock. This weathering releases ions such as calcium, magnesium, bicarbonate, and sulfate into runoff, which then carries them into rivers, lakes, and coastal seas. The high availability of reactive minerals and the increased flow of water can lead to pulses of enhanced weathering and nutrient delivery, affecting both the carbon cycle and ocean chemistry. In shallow marine environments that fringe deglaciated continents, these changes support rapid precipitation of carbonate minerals. The resulting carbonate rocks, often described as cap carbonates, when they sit directly above glacial deposits, record these conditions. They typically show textures and geochemical signatures consistent with high saturation states of seawater with respect to carbonate minerals, and with strong fluxes of dissolved inorganic carbon. Their presence in many regions suggests that post-glacial oceans at least locally hold elevated concentrations of dissolved carbon species, and that carbonate precipitation is an important pathway for removing some of this carbon as the system readjusts. At the same time, organic productivity in surface waters responds to the combined effects of warmer temperatures, renewed nutrient inputs from land, and changes in mixing and circulation. Cyanobacteria and eukaryotic algae in newly opened photic zones can increase primary production, fixing carbon dioxide into organic matter, and in the case of oxygenic photosynthesizers, releasing oxygen. When part of this organic matter is buried in sediments rather than respired, it constitutes a net sink of reduced carbon and a net source of free oxygen to the atmosphere-ocean system. Post-glacial intervals may therefore include periods when organic carbon burial is relatively high, contributing to further rises or stabilization of oxygen levels in surface environments. The structure of the oceans adjusts as stratification circulation and redox gradients reorganize after near global ice cover. As sea ice retreats and exchanges of heat and gases with the atmosphere increase, oxygen can enter surface waters more effectively. Winds and density-driven flows mix these oxygenated waters downward into the upper and mid-depth ocean, deepening the oxic layer compared with Snowball Earth states. In some basins, improved ventilation may reduce the volume of anoxic or ferruginous waters and modify the positions of redox boundaries. However, deep ocean conditions remain influenced by the balance between oxygen supply from the surface and oxygen consumption by the decomposition of organic matter, and in many regions anoxia likely persists at depth. The exact extent and timing of these changes vary between basins and through time, but the overall trend after major glaciations is toward more stable oxygenated conditions in surface and shelf waters. These physical and chemical shifts have direct ecological consequences for microscopic life and for the early emergence of more complex organisms. In surface oceans, stable and more extensive photic zones with reliable seasonal patterns support diverse communities of photosynthetic microorganisms. Eukaryotic algae expand in abundance and distribution, contributing more strongly to primary production in some settings than before. Heterotrophic protists, including flagellates and ciliates, graze on bacteria and algae, forming more structured microbial food webs. The increased availability of oxygen in surface and near-surface waters allows aerobic metabolisms to operate more widely and efficiently, providing more energy per unit of organic carbon consumed than anaerobic pathways. This energetic advantage can support larger cell sizes, more complex internal structures, and eventually simple multicellularity. On continental shelves and shallow platforms, newly flooded areas over glacially sculpted topography provide habitats for benthic communities. Microbial mats re-establish themselves on soft sediments and carbonate substrates, but in some sequences of late Proterozoic age there is evidence for the presence of soft-bodied macroscopic organisms that occupy these environments alongside microbial structures. These organisms, often grouped within the Ediacaran biota, include forms that appear as impressions or casts in fine-grained sediments. Their exact biological affinities remain under discussion, and they may represent a mixture of stem group animals, algae, and other eukaryotes. Regardless of their specific identities, their occurrence in post-glacial and Ediacaran rocks indicates that the ecological space for larger multicellular life on the seafloor is beginning to open, likely facilitated by more stable oxygen availability in shallow marine settings, and by the accumulation of organic matter that can support heterotrophic lifestyles. In the water column, planktonic ecosystems also show signs of increasing complexity. Fossil assemblages of certain organic walled microfossils suggest that eukaryotic plankton diversify in the later Proterozoic, with a wider range of sizes, shapes, and wall structures. These changes may be linked to shifts in nutrient regimes, redox structure, and grazing pressures. For example, higher nutrient inputs following deglaciation can support more productive blooms of algae, which in turn may favour the evolution of larger or more heavily armoured cells as a response to predation. At the same time, oxygenated surface waters allow aerobic respiration to sustain more active lifestyles and faster growth rates for heterotrophic protists and simple metazoans that feed on plankton. The cycling of carbon, sulfur and other elements reflects the new balance between sources and sinks established after Snowball Earth events. Enhanced weathering on deglaciated continents temporarily increases the supply of sulfate and other ions to the ocean, supporting vigorous microbial sulfate reduction and sulfide burial in some regions. Increased burial of organic carbon and sulfides when combined can allow further net accumulation of oxygen. Stable isotope records of carbon and sulfur from late Proterozoic rocks show sizable excursions indicating shifts in the relative rates of these burial processes and in the redox state of the oceans. Some of these excursions occur near the boundaries of glacial and postglacial intervals and are interpreted as signatures of rapid system-wide adjustments in element cycles during recovery. Through these combined processes, late Proterozoic Earth moves toward a state in which oxygen is more consistently present in the atmosphere and in at least parts of the ocean, though still at levels below those of much later times. Surface climates after major glaciations settle into conditions that are temperate on average, with open oceans, active hydrological cycles, and limited but still possible glaciation at high latitudes or elevations. Continental shelves host carbonate platforms, microbialites, and early macroscopic communities, while deeper basins retain redox stratification with anoxic or ferruginous conditions in many areas. The biosphere remains dominated by microorganisms, yet multicellular eukaryotes are beginning to occupy a broader range of ecological roles, particularly in shallow marine settings. These developments occur within the constraints set by the Proterozoic context: a slowly brightening sun, an atmosphere that has transitioned from near anoxia to modest but persistent oxygenation oceans that are still partly anoxic at depth, and continents that continue to assemble and rift, creating new basins and habitats. The postglacial recovery states do not erase the memory of Snowball Earth intervals, but build upon them using the altered distributions of carbon nutrients and redox states as starting points for further change. By the end of the Proterozoic, as the Ediacaran period unfolds, the Earth system thus exhibits a combination of physical stability at large scales and biological and geochemical dynamism at smaller scales, setting the conditions under which later chapters of Earth's surface evolution will proceed while remaining fully within the bounds of the Proterozoic Eon itself.